Okay, all right. Well, welcome everybody to today's Consciousness Club. Good to see lots of people online. So we're really glad to be having with us today Clare Press, who's our UCL colleague. She's head of the Action and Perception Lab at the Department of Experimental Psychology and a PI at the Functional Imaging Lab at UCL. She did her undergraduate at UCL in psychology before undertaking her PhD with Celia Hayes. And then she went on to do postdoctoral fellowships, both with Cecilia and then moving on to work with Martin Eimer at Birkbeck and then at the Phil with James Kilner and Carl Friston. She then took up a faculty post at the University of Reading before moving to Birkbeck. And then recently, in 2023, she moved to EP at UCL, where she's now a professor of cognitive neuroscience. So Claire, we're very excited to have you join us and give today's Conscious Club. So take it away.
Thanks very much for inviting me. So what I'm going to be speaking about today is how we're generating our perceptual experiences via our learnt knowledge of the world and such that those perceptual experiences can then in turn go back and inform future learning. So first things first, what is wrong with old accounts of how we basically perceive the world? So if we go back several decades, it was assumed that perception was supported solely by what I'm calling here bottom-up information processing in the brain. So you'd have patterns of light hitting the retina or stimulation of the eardrum, pass this information up a hierarchy in the brain to generate an awareness corresponding to that particular taxi in that particular location. But it's been realised more recently that that view of perception doesn't really work, given the number of imperfections that this would generate for us. So first of all, under this view, perception would be always out of date. So what you need to think about here is that the brain takes time to transmit information, say from the retina and the eardrum, to structures that can help generate awareness of those events. At least 100 milliseconds, according to some accounts more like 400 milliseconds. That combined with the fact that our environment is continuously changing, so the taxi's always moving, our boat's always moving in the river as we row up it, the position of the ball is continuously moving as we play cricket. If we generate percepts in a wholly bottom-up fashion, then they're always going to lag the environment. Some of the time this won't matter, but some of the time it really will. So for example, when you're trying to hit this ball in cricket. It's also the case that what's hitting our sensory receptors is incredibly noisy. So if you consider yourself speaking to your friend on the tube, then what is hitting your eardrum is not going to be a perfect reflection of their speech stream. It's going to be corrupted by noise from the carriage moving within the tube tunnel. It's going to be corrupted by other people holding conversations. Our experience actually is pretty noisy too, but it's not as noisy as what is actually hitting our eardrum. It's also the case that we've got limited capacity processing systems, and basically we can't process everything. There's so much information across space and across time, and you can't generate an experience corresponding to all of it. So for example, this black van will be generating an impression on your retina, but it's not then necessarily generating an experience of that van situated there. So perhaps a purely bottom-up account is not going to work. It's going to be too imperfect in terms of what we experience. How can we overcome some of these problems? So what's been agreed among a lot of perception researchers, arguably a majority, across the last few years, is one of the especially powerful ways in which we can overcome some of these problems is to learn about the statistical regularities within our environment and to use that learnt knowledge to make predictions about what we're likely to see and overcome thus some of these problems. So for example, I know from when I played cricket before and from watching balls move that when I swing my arm out towards the ball, I'm likely to see a ball moving off in a particular trajectory. I can also predict based on my experience with cars, that I'm likely to see windscreen wipers at the bottom of a windscreen. We use all of this learnt knowledge to shape perception in important ways to overcome some of these problems. The difficulty comes in that we're not very sure how. So there's an awful lot of accounts out there on the table across different domains of sensory cognition, all appear to be doing very useful things and seeming highly plausible, but actually lots of them just don't fit together. And so we're at the state of knowledge at the moment whereby we know that the learnt knowledge is shaping perception, but just exactly what this influence is really quite hard to be sure about. So what I'm going to do in my talk today is to present to you some work that we've been conducting to try to answer those questions. The first part of the talk will be familiar to you if you've seen me talk in the last few years. It's a line of work that we've had going on for some time now, whereby we're asking about predictions concerning content. So predictions about what I'm likely to see, predictions that I'll say see a polar bear in the Arctic, how those are shaping our perceptual experiences in a way that we can optimize both for veridicality, so this is accuracy of experience, and also informativeness of experience, so telling us when the world is not as we thought it was going to be. The second part of the talk is brand new, in fact. I've never presented this line of work at all. It only started a year ago, so you're probably going to notice quite a change in fluency when I get to this part. This is concerning predictions about time. So we can predict when in time important information might be presented. And we're asking how this is determining fluctuations across time in processing in the brain and in turn our perceptual experiences. So to take the first part, so predictions about what I'm going to see. What effect might this have on our ultimate perceptual experiences? One of the possibilities has been put forward in what I'm calling here Bayesian theories, so often couched in Bayesian frameworks. These theories are popular across a wide variety of domains of sensory cognition, so especially amongst vision neuroscientists, asking how we process edges, asking how we process polar bears within the scene that they're presented in. Also auditory neuroscientists, so asking how we process speech streams and other auditory information. What's proposed in this account is that we learn about what is likely to be out there, and we have the incoming sensory evidence, and we take what's called a precision-weighted combination of those two sources of information to determine the ultimate percept. So by precision weighting, I mean according to their reliability, such that if we have an especially reliable prediction, we're very sure what we're likely to see, and a less reliable sensory information, then we're going to bias perception more towards the prediction. If we have a more reliable incoming sensory input, then we bias things more towards that sensory input. But importantly, what we're ultimately perceiving is lying somewhere between those two sources of information for us. What this process results in is what I'm calling here an upweighted perception of what we expect. So we're more likely to perceive it, and we're perceiving it more intensely because this learnt knowledge is directly feeding into what we are experiencing. The adaptive arguments put forward for why this type of mechanism would be useful to us in terms of overcoming some of those problems highlighted with the bottom-up accounts is that it's going to help us to generate more veridical, so more accurate experiences, and rapidly. So this is based upon the assumption that what we've learnt is likely to be there, and therefore we expect to be there, is actually more likely to be there. So for the most part, our environment has a lot of regularity that then continues. So if you bias your perception in line with those learnt likelihoods, it will tend to render perception more accurate. And it's also going to allow us to get there faster than if we're relying on this bottom-up stream that may take sort of several hundred milliseconds to process. So to highlight the logic here, I might be walking home one evening and take a glance up the path in front of me and be presented with something that looks like this sort of cartoonized input panel here. So basically it's dusk, there's not brilliant sensory information, but also I've taken a quick glance, so I haven't given myself much opportunity to gather all of it. So I have a noisy input, but I have an expectation that I should see my sons in front of me. And therefore, if I combine this expectation with this noisy, quickly acquired input, I arrive at a more accurate experience concerning what is out there than if I rely solely on this noisy input. So a brilliant account of how you can generate more accurate experiences rapidly in the face of sensory noise and in the face of these neural transmission delays. Brilliant account, but in fact lying in direct opposition to accounts that you see elsewhere in the sensory cognition literature. So these accounts I'm calling cancellation theories. They're sometimes also called attenuation or dampening theories. They're especially popular in the action perception literature, so asking how we're using our motor commands to shape our sensory experiences of the environment on the basis of the predictions we can make due to those actions. What's proposed here is that when we've predicted what is likely to be out there at the sensory level, we attenuate this information within what we perceive. So instead of these Bayesian accounts, it's proposing then that we have a down-weighted perception of what we expect. So we perceive it less intensely, we're less likely to experience it because we've attenuated this information within the sensorium. So there's lots of data supporting these accounts, like lots of data supporting the Bayesian accounts, but to put it in context for those of you from a different field, one of the examples often used to just highlight this theory as a memorable type of example is the fact that we cannot tickle ourselves. So what's being assumed here is that we, when we move our fingers lightly across our skin surface, we predict the sensory input that is likely to ensue when we send those motor commands, and we perceive this input less intensely, less readily than if someone else was to unexpectedly tickle you. Given an opposite mechanism is being proposed to that highlighted by these Bayesian theories, it's therefore no surprise that the adaptive function this type of mechanism is proposed to serve is somewhat different from that highlighted in the Bayesian account. So instead of making accurate experiences in the face of noise and in the face of neural transmission delays, what this is supposed to do is to yield informative experiences for the organism. So by relatively turning down the volume on what we expect, this is yielding more resources in our limited capacity system to process what we do not expect. And it's what we do not expect that's actually telling us something. It's telling us that we need to update our models of the world or learn what's the point in perceiving what we expect. So what we wrote about several years ago then is if you think about these two theories, they're highlighting a paradox. So the mechanisms that are being proposed under these Bayesian accounts, which effectively turn up the volume on what we expect, will be optimizing accuracy of experience while directly acting against informativeness of experience. So that is, we'll actually be less sensitive to those elements in the environment that are not in line with our expectations that should tell us we need to update our models. Conversely, if you think about these cancellation accounts, by relatively turning down the volume on expected channels, this is going to render us more sensitive to when the world changes, but it's not necessarily going to lead us to have very accurate experiences because we're effectively sort of processing the error signal. This is probably not very in line with how the world is, especially when you consider that we have noise in our inputs. Relatedly, of course, so that is the theoretical paradox highlighted in bold here. We need our experiences actually to be both accurate, quickly generated, and informative, and it seems like the mechanisms being proposed to achieve one are directly acting against the other function. We also have an empirical paradox, which is that these accounts have all been supported by decades of data. So why do we have all of these findings in opposing directions? What's really going on? The first thing that we started asking, and I'm going to try to condense this line of work so that to make space for some newer work, is that it might be different in action. So that is, the accounts that I've shown to you grew up in these different fields, the cancellation accounts in the action literature, these Bayesian accounts outside of action. Therefore, one might suppose it just works differently in action. In fact, when we were thinking about this question several years ago, it wasn't immediately clear to us why it should be different in action. So if you consider the adaptive arguments, then we need our percepts to be accurate, quickly generated, and informative, regardless of how we're forging those experiences. So if you just take the example of action, when I'm acting upon the world around me, all of those functions are incredibly important to us. We need accurate experiences in the face of an awful lot of noise, certainly when we are moving. It's also the case that, okay, you've got all this data in the two domains, but it was premature to conclude that empirically think there's just evidence that things are working differently because different empirical approaches have been taken. So the theories conflict, but actually not the data, because they've used different types of evidence to support these conflicting accounts. So what we did, just as a first step to say what's really going on here, is to take those approaches where the classic Bayesian effects have been found in vision and audition to the domain of action. So to ask, is it really working differently? I'm not going to give you the details of all but one of these studies, but basically now, in a nutshell, we get Bayesian effects on perception and Bayesian effects on neural processing when we're taking those paradigms that have generated these Bayesian effects outside of action. So now action is the cue that's providing us information about what we're likely to perceive. But so in terms of asking what people are perceiving, basically across vision, audition, and touch, we're finding that you're biased towards perceiving what you expect on the basis of your actions. You're more likely to perceive it, you're perceiving it more intensely. If you look at the neuroimaging findings are also falling out in line with these, what has been found basically outside of action. So I'm going to unpack for you one of the studies that we've conducted with neuroimaging to give you a flavour of this type of evidence that we're talking here then for how we think things really might be working. So the neuroimaging evidence that is often used to support these cancellation accounts is that when you're acting on the world, you have a lower sensory signal that's associated with presentation of sensory events that were predicted on the basis of concurrent actions. And this is interpreted as attenuation of expected activity and thus evidence for this cancellation account. So this is seen in somatosensory cortex when processing tactile outcomes, visual cortex when processing visual outcomes, and auditory cortices when processing auditory outcomes. The issue is that this isn't the only interpretation of this lower signal. So something that was highlighted by Peter Koch, Janneke Yehey, and Floris de Lange in 2012 was a lower signal associated with presentation of an expected Gabor patch. This Gabor patch has not been expected due to action, but the basis of a preceding cue. But that this lower sensory signal was not looking like it was generated by a cancellation type mechanism. So what do I mean here? Right, now what you need to think about is that all of our sensory systems have populations tuned towards different types of sensory features. So I'm going to show you the logic here for primary visual cortex that's especially responsive to orientation of edges, but the logic also applies for any sensory region. What I'm showing you in blue is what you might expect under some hypothetical baseline when you're just observing vertical edges. So that is more activation in the populations encoding the vertical relative to the off vertical. What's being shown in red is what's being assumed under the cancellation account to generate this lower sensory signal, which is that when you're expecting this vertical edge, you basically turn down the volume in the channels representing the expected, thus leading to this lower overall signal. An alternative that was proposed in Peter's paper in 2012 was that instead, when you're expecting this vertical edge, so shown in red here, instead you activate the populations encoding the vertical, so turn up the volume on these channels, and via some lateral inhibition process, relatively suppressed processing elsewhere. And this is called the sharpening account, which is arguably more in line with Bayesian effects on perception, so biases towards perceiving what you expect rather than away from. And importantly, why it was proposed was that it was also more consistent with the other patterns they were seeing in the neural data. So there's a lower signal, but actually when they trained and tested pattern classifiers on the basis of that information in primary visual cortex, they were performing with better accuracy in the expected condition relative to the unexpected condition. So this is in line with this graphic here, where you basically have a crisper, sharper representation of what you expect, less consistent with this cancellation graphic highlighted over here. So what we wanted to do was to take that logic to the domain of action. So now action is providing you your cue about what you are likely to perceive. So this was a study that was led by Daniel Yon, who was in my group for several years. And what he did was to generate action predictions by requiring participants to abduct their index or their little finger, and they would be observing an on-screen avatar that's performing synchronized movements with their own. So, for example, an expected trial would be that the participant abducts their index finger and the on-screen avatar abducts its index finger. An unexpected trial is the participant abducting their index finger and the avatar abducting its little finger. And he then asked, where across the visual hierarchy is responsive to this difference between index and little finger movements? And basically then, if you're training and testing pattern classifiers on the basis of that information, are they performing with better or worse accuracy when those visual outcomes were expected relative to unexpected? What he found, in line with Peter's Gabor study, was across the entire hierarchy that is responsive to this difference. So occipital regions, occipitotemporal regions, we're getting better classification accuracy when those outcomes are congruent with the motor commands you just sent relative to incongruent. So meaning when they are expected on the basis of that action that you just performed. We also want to look at the univariate signal to further try to understand what was going on here. So in order to distinguish between these accounts, we can't just look at overall levels of the signal, because it would be expected across accounts that you have this lower signal for expected trials. But what we wanted to do was to split the voxels according to whether they're more responsive to index or little fingers, to ask whether the lower signal is coming from the voxels that are especially responsive to the thing you're looking at, or the voxels that are more responsive to other things. And what we found across the board, so all of these regions, is that we're getting no sign whatsoever of a lower signal in the congruent relative to incongruent trials in the voxels that especially like that thing that you're looking at. In fact, all of the effects are the other way. They're actually more active when you're seeing the expected relative to unexpected outcome. All of this lower signal is coming from the voxels that prefer other things. So this is in line basically with this sharpening idea of what's going on, where all of this lower signal is coming from the off-center rather than the center. Most importantly too, it's consistent with what has been found in visual cognition when action has got nothing to do with it. You're simply seeing Gabor patches and predicting their orientation based on other sensory information, so preceding tones. So this led us to think mechanisms probably aren't then working differently in action. We were tending to think they probably wouldn't do anyway because of these adaptive requirements. But now at an empirical level, it's really seemed that we're in a position to say probably not. We've now got comparable empirical approaches and we're getting comparable answers. So what this led us with was the knowledge now that we have a problem to solve across sensory domains concerning how we're both optimizing for accuracy of experience whilst telling us very well when the world is not as we thought it was. So that is, if we're completely optimizing for one, we're completely sub-optimizing for another. And how do we, to the best of our ability, basically do both at once? This is hence my title of the talk. So we're learning about the regularities in order to help us perceive, but we're also then using that perceptual knowledge to help us to learn and update our models. So we have this continual iterative loop between perception and learning. What you'll note is that I've therefore shown lots of evidence in line with this Bayesian account. So the particular neuroimaging study I've shown you is in line with this sharpening type mechanism, which is basically amplifying sensory gain of expected channels, and lots of psychophysical data then showing biases towards perceiving what we expect and that we're perceiving it more intensely. I've also shown how some supposed support for cancellation accounts can come about just via alternative interpretation of some of those data, so with the sharpening mechanism rather than a cancellation mechanism. But there's also other cancellation findings at the level of perception and at the level of some neuroimaging too that are suggesting it's more complicated than that. So we have got some types of mechanisms that are going to be sometimes rendering us more sensitive to what we do not expect. And we're also assuming then that we need these mechanisms because we need to render what we experience informative. So we really do need to remain sensitive to information that tells us that the world is not as we thought it was. So how do we do it? So we don't think it's via a cancellation mechanism. As I say, this would pull you against accuracy of experience, and I've shown you lots of data that then suggest that it's, yes, probably not working like that. So what do we think is going on? One of the things that we highlighted in this paper a few years ago is that we think it's going to require consideration of whether a so-called unexpected event is particularly informative. So, for example, lots of error signals are continuously bombarding us. So every single millisecond, we're going to have sensory information that's coming in that's not precisely as we thought it was going to be. But actually, most of those error signals are not reflective of the environment being different from how we thought it was going to be. Much of that is actually just sensory noise. And some of it, too, is just learned variability within the environment. So we might have a modal prediction, but we'll have learned variability around that to say that actually a variety of things can still come in. This is very different from the type of situation where we're just ambling around the Arctic, as you do, expecting to see polar bears, and we suddenly see an elephant. This is completely out of line with what we thought was going to happen, and it means our models of the world really were very wrong. So what we proposed is that much of this mechanism is going to require us distinguishing between was this error signal due to noise, or was it due to information that the world had changed? If we have the complete answer here concerning how we would perform this separation, then I think the learning community, some of them could pack up and go home. It's a very, very difficult puzzle to solve. But one of the things that we proposed is a difference between error signals due to noise and error signals due to the world is different is actually the level of the error signal. So the level of KL divergence between your distributions concerning how you thought the world was before the input came in and how you now think the world is after the input comes in. So what we noted is that the Bayesian effects in the literature, so where you're biased towards perceiving what you expect, are often seen when you have a weak sensory signal. And what this is going to be generating is actually a fairly high level of overlap between your prediction and the sensory information, such that you don't really change your model of the world when that sensory information comes in. So we have low KL divergence between these distributions. When you see cancellation effects, we found these cancellation effects are far fewer and further between, but these are associated with a higher level of surprise. So, for example, they will be associated with a stronger signal. Signal detection paradigms are not very common in the action community. The reason this matters then is that with a high precision input, you're going to generate a larger deviation between how you thought the world was before the input came in and afterwards. And so what we thought was that cancellation effects then appear to emerge perhaps when you have this larger error signal. And why do we think this larger error signal matters? Now, something we were also becoming quite focused on was work from the computational learning community that's seeming to find processes that operate reactively to the presentation of surprising events that is thought to facilitate learning. So the types of process I'm talking here, for example, lots of work by Peter Diane over the years, but phasic release of catecholamine, so dopamine, noradrenaline, when you present something surprising, so very rapidly, so 80, 100 milliseconds later, and behavior in relation to this, so for example, saccades to the unexpected, pupil dilation in reaction to it. These processes are thought to optimize learning, so optimize plasticity of the brain, updating of connection strengths, because if you block these processes, you don't learn as readily. What we noticed too, though, was that there's some evidence independently in a perception community that at the tonic level, if you're increasing noradrenaline, this is amplifying the SNR within the thalamus. And so therefore, what we thought is possible is that these phasic effects are having a similar influence to the tonic effects. So maybe you're getting this learning boost via a perceptual boost. So when you have some broad brush error signal that says the world's not as you thought it was, you effectively amplify this sensory gain to allow you to then generate a high precision representation of what is out there to enable accurate model updates. And we propose that this might only be invoked by highly surprising events. So when this error signal is coming in and actually is in line with sensory noise, then this does not elicit this process. It's only when really the information that comes in is not consistent with what you had previously learned. We therefore proposed a tentative resolution to this paradox that might therefore help you to generate both accurate rapid experiences and informative experiences. Importantly, you really can't have your cake and eat it. You can't completely optimize for everything, but this was our best working account of how you might do your best at optimizing across those features that you need to. So what we said is that we have opposing processes that help us to achieve this. The first of which is that prediction is biasing perception towards what we expect via activation of expected sensory representations. So this is something akin to this sharpening mechanism that I presented to you before, which will generate broadly accurate experiences for you and rapidly. However, so most of the time, this is all that happens. Most of the time, our best guesses are correct, but we sometimes have these inputs that are really out of line with what we had learned about the world structure. So not all error signals, but those large enough to elicit noradrenaline release. This means that we will have the elicitation of reactive processes which amplify sensory gains, generate a superior representation of these events for model updating. Now, we're conducting many lines of work actually to try to figure out whether this might be how it works and generally how learning and perception go together. But just to tell you about a couple of the lines of work before I then move on to the second part of the talk. So first of all, actually, so we're conducting lots of time-resolved EEG decoding, so led by Kirsten Mittershoff in the group. What I decided to do was actually tell you about a study from another group who wanted to test this account too, so a paper that came out last year. What this group did, so Richard Kasper and Federico, along with Hannah McDermott, is to basically present image pairs with different transitional probabilities. So you have trailing images following leading images, and then you can present expected or unexpected versions of those and basically ask about the neural processing of these across time. And looking at using decoding to basically ask about the content of that signal. What they found was that if you look across time, you're getting this expected flip across time that would be anticipated due to our opposing process account. So if you're looking early in processing, about 150 milliseconds after you've presented these trailing images, you have superior decoding of the expected than the unexpected, but this is flipped by more like 300 milliseconds. Well, in fact, sort of starting earlier than that. So this provides actually some very nice neural evidence in line with our account that perhaps we're optimizing all of these functions by basically having some super early processes that bias us towards perceiving what we expect and generate best guesses rapidly. But we then have some reactive processes that once they've been elicited, allowing us to turn up the gain on some of these unexpected signals. So as I say, we're continuing along the lines with lots of that work ourselves, varying precise probabilities, looking at actions as predictors. And I can tell you how that goes when we finished the work. We've also got some work actually that's asking how we fit all of these accounts into ideas about how the brain works that are assuming populations with different roles within particular sensory regions. So what's been proposed within predictive processing frameworks, there are different varieties of these, but a commonality is that you have units with different roles that are supporting this integration of the learned knowledge with the incoming sensory stream. So a particular popular version of these accounts is that you have predictions that are fed back to deep sensory layers and stored in what are called hypothesis units. Sensory input comes to middle layers, and then you have a discrepancy signal represented in superficial layers in what are called error units, fed back up the hierarchy to update these predictions. There's evidence of operation of these mechanisms in animals that aren't humans, but what we wanted to do was to take 7T MRI to ask whether this is the pattern that we might see in humans. So with 7T MRI, we can now have a resolution such that we can distinguish processing in different layers. But so like with the earlier study I showed you, we can train and test pattern classifiers to ask whether we have different types of representation across these layers. So have we got better representation of the expected, the non-expected and deep layers where we have these hypothesis units, but the opposite pattern in superficial layers where we have these error units? And indeed, we do seem to have some evidence along these lines. So I'm going to tell you a bit about this study that was led by Emily Thomas. So what she did was to generate expectations via training between actions and Gabor outcomes. So in training, every time they abduct their index finger, they see a clockwise oriented Gabor, clockwise from vertical. Every time they abduct their little finger, they see a counterclockwise oriented Gabor. And then we reduce this contingency. So they're answering questions about the Gabor. We then reduce this contingency during test in the scanner to include some unexpected events. So 75% of the time, what they'd learnt in training continues to be the case, but now 25% of the time they get the opposite Gabor. And we then have a localizer at the end where we train a classifier to distinguish these Gabors and then ask how it performs across layers and across expectation category in the main task. In a nutshell, Emily found exactly what I just presented to you might have been found under these predictive processing accounts, such that we've got superior representation of the expected, the non-expected and deep, where these purported hypothesis units reside, no difference in middle where the purported input is represented, and better representation of the unexpected and superficial, where purported error signals are thought to reside. So this is in line with this classic predictive processing account. What we're currently doing is asking how this processing in these different unit types is corresponding to our unitary experiences. So we can't have experiences corresponding to all unit types simultaneously. It's been suggested that the belief units are corresponding to what we perceive, assuming that our perception is our beliefs about the world, and therefore that processing in the deep layers might be corresponding to our experiences. And it's also the case that we want to ask how this error processing is relating to midbrain processing, specifically in the locus coeruleus, that might be responsible for many of these catecholinergic processes that we are interested in. So that is work that Nick Simpson is currently leading, but which, we don't yet have the answer to. So broadly, as I say, we've got this idea about how these content-based predictions might be shaping what we experience. What I want to turn to for the last part of the talk is consideration of temporal predictions and how these might be shaping fluctuations in our experience across time. So as I say, this is a very new line of work. To tell you exactly what I mean by temporal prediction, and what I mean by temporal fluctuations, then something you will be very used to considering if you're an auditory neuroscientist is that our sensory environment is continuously changing moment to moment, and there are information peaks in this stream. So if you're listening to someone speaking, for example, you're listening to someone saying a very interesting sentence, David examined 5 beautiful paintings, then this stream is continuously changing moment to moment, but it's changing at a fairly regular pace depending on the speed of talking of the speaker. So Depending on who you're listening to, if they're a very fast communicator, then they're going to be having syllables coming in at about 6 hertz. If they're really sluggish and slow, then it's going to be more like 2 hertz. And basically, so we have peaks in this information stream across time. So every time the syllable changes, we have more information than when it's ending. What you might think about less if you're a visual researcher is that actually this is also true of vision. So of course in the lab, we can stabilize our visual environment and just give people really boring tasks where they just have like one Gabor patch on the screen for 3 seconds. This is not how our visual world really is. So I'm probably saying this as an action and perception researcher, but there are an awful lot of temporal regularities in our visual sensory streams too, as we interact with it. So as we run along, walk along, as we type on the keyboard, we're typing at a pretty regular pace. And every time we hit a key, a letter is appearing on screen. If we're playing the violin, not only will we hear the sounds, but we're going to be seeing very regular movement of our bow. We're going to be seeing the conductor's baton at fairly predictable moments in time. What's also the case is that our brain is changing its activation profile across time in lots of interesting ways. So if you perform frequency decomposition of the signal, then you're going to see structure at a range of frequencies. So in very low frequencies, so delta and theta below 5 hertz, also going up to alpha, beta, and gamma. Of course, many debates concerning what all of this means, but what we do know is that these fluctuations are also determining fluctuations in perception. What we've been quite interested in is how we align the two. So looking with these coupled oscillators, then we might have fluctuations in the sensory input stream. We've also got fluctuations in how the brain is processing information. How do these two couple together to basically best process the incoming input? Now, in a paper we just submitted last week, and it's the focus of this grant we've started working on in the last year, what we've been focused on is trying to think about 2 very prominent accounts that seem like they basically are both doing useful work, but probably need integration in some way. So due to the fact that they both seem very sensible, but can't, strictly speaking, both be true at the same time. So the first type of account is what I'm calling here a flexible theory. So these are often called entrainment theories or rhythmic tracking theories that are especially popular amongst auditory neuroscientists. So people studying speech, people studying how we perceive music. And what is proposed here is that the oscillations in our brain are driven by the external sensory information, such that if we're hearing syllables coming in at about 3 hertz, or we're hearing musical notes coming in with a beat of 2 hertz, then this information is causing our brain to oscillate at 3 hertz, even when you remove that sensory information, and this is generating then peaks and troughs in our perceptual sensitivity. And these seem very elegant accounts, basically, for how we're going to be aligning our neural processing with where we are likely to have information. So if the syllables have come in at 3 hertz, it's quite likely they'll continue coming in at 3 hertz. So if we align our maximal sensitivity with where this information is likely to come in, then this is going to optimize perception. If you turn to vision, you have actually quite popular accounts that are seeming to say something quite different from this. So in many theories that I'm calling here fixed theories, they're often called intrinsic theories. What is proposed instead is that you present something static on screen, and you're seeing these fluctuations across time in perceptual sensitivity and in oscillatory structure in the brain. So what is being proposed is that you have these rhythms that are determining perceptual sensitivity, but they're independent of the sensory stream. So you're seeing fluctuations often at about 4 hertz, but you're not presenting input that is fluctuating at 4 hertz. So rather than there being an external driver, what is being proposed is that these result from natural, intrinsically determined frequencies, not agreed upon concerning where they come from, but seem 2 prominent accounts on the table, first of which is that they're generated by receptive field interactions in sensory cortices, and the second of which is that they're generated by motor rhythms. So for example, saccades. So they're found when you're not moving your eyes, but it's said that maybe these result from motor rhythms of saccades, so as if you are covertly exploring your environment. What we've been thinking about basically is that we don't really think sampling mechanisms should operate so differently across modalities. So you can't say they're fixed and they're flexible. It seems that actually both of these lines of work are probably giving useful information across the Century board, but we need to think about how these ideas really could fit together. Something that we've been especially fascinated by is that the visual world is containing these temporal structures too. As I said, with like typing at the keyboard, walking along the pavement, playing the violin, any fixed rhythm probably won't perfectly align with any of this external structure, and therefore might not be optimized for picking up really on the true information peaks. It's also the case that we have motor rhythms and receptive field interactions which should influence visual processing, but also auditory processing. So any of these fixed receptive field interactions are going to be determining auditory processing too. And also motor rhythms, perhaps not saccades as much as in vision, but speech rhythms should really be changing our sensitivity to this sensory information. Something we've also thought about is that actually it's quite maladaptive to be completely flexible. So some of the debates in the entrainment line of work in audition are coming about from the fact that you can present sort of 6 events in a row at 3 Hertz, and you don't then see the brain oscillate at 3 Hertz after that. In fact, perhaps this shouldn't be very surprising. If you're a learning researcher, then you'll be preoccupied with the debate of the extent to which actually you should be learning about new structure in the world, because the extent to which you learn about that is going to be dependent upon your beliefs concerning environmental volatility. So you are going to be driven by potentially sensory noise if you're always just driven by this external sensory input. What's worth noting is that there are many controversies surrounding these existing accounts. In many respects, don't want to jump on the bandwagon, but in fact, what we think is that there's very useful work being conducted in both of these lines, and that actually the rethinking that's required is actually how these can both sit together. So what we proposed in this article we just submitted last week was taking the type of logic that I've employed in the first part of the talk to describe expectations about content to expectations across time. And what we've proposed is that our sampling rhythms, and hence fluctuations in perception, reflect statistical learning of the temporal properties of our inputs that are determined both by externally and motorically determined sensory dynamics. So as I've said, you can present information, say at 2 Hertz, both in audition and in vision, but actually the motor commands that we are producing are generating sensory fluctuations across time too. So this is easiest to comprehend perhaps if you think about saccades. We do saccade at 4 Hertz, it's the most common frequency in terms of the work I've read anyway. If this is the case, we spend a lifetime saccading at 4 Hertz, we actually learn to expect visual information at 4 Hertz, because every time we move our eyes and fixate on a new piece of information, this generates a peak in the information stream. So actually, even if you're not saccading, you could have a really stubborn prediction that information should fluctuate at that rate. By yoking this idea with the Bayesian learning literature, we're also setting bounds on when we should expect to adapt to this external structure. So that is, it could perhaps overcome some of these debates in the entrainment literature surrounding the fact that you don't always entrain, but you do sometimes. So the extent to which you're going to adapt to this external structure should be determined by your learning rate, which is determined by your beliefs about whether you expect preceding structure to continue or not. So to give a bit more information about what we're proposing here, we're therefore proposing under this Bayesian logic that we're processing the sensory world according to the probability with which all our sources in a precision-weighted combination have predicted information at that time. This doesn't need to come just from our recent experience, it can also come from across the lifetime. So if I show you this graphic here, What I'm showing you in the top row is where we just have a source of information that's predicted information at 4 Hertz. So this is a second here. So we basically, for example, might have a light flashing at 4 Hertz. This is just a cartoonized demonstration of information coming in at 4 Hertz. What this would lead to is basically 4 Hertz oscillators that can then pick up maximally on the information in that input stream. Most of the time, we have more than one source that provides us with information about what we're likely to perceive. What I've shown you here is the situation where we've still got that very reliable 4 Hertz source, but we've now got a less reliable 2 Hertz source. So for example, we've shown this with a traffic light here. So it's approximately the information's coming in at 2 Hertz, but not exactly. So these are slightly misaligned with the line that's demonstrating you the 2 Hertz information. So what this is meaning is that we have a 4 Hertz source and a 2 Hertz source, but the 4 Hertz source is more reliable. So we basically have both of those 2 Hertz and 4 Hertz powers contributing to the extent to which we're sampling information across time. And then the bottom row is just showing you the other way round of this. So we have a very reliable 2 Hertz source and a less reliable 4 Hertz source that is again determining this oscillatory structure, but with more precision now on the 2 Hertz source. So this is just an idea at the moment, and it's a line of work we've just started on, but I'm going to present to you in the last few minutes a line of work that we've conducted to try to start understanding whether this is how it works. And as I said, one of the things we've been particularly interested in understanding with respect to whether we really need to integrate these lines of work is whether it's really working similarly in audition and vision. So a natural starting point seemed to be asking whether we can get these externally driven oscillations in vision in the same way that they have been seen in audition. So this is a line of work that's being led by Aaron Kaltenmeyer, a PhD student in the group, and also with Quirin, who's a postdoc. And so what we have been doing is to ask, so in audition, what's been found is that if you present syllables, say at 2 Hertz, your brain will continue oscillating at 2 Hertz in a window afterwards, so allowing you to control for evoked responses. You will continue to have this oscillatory response at 2 Hertz. And this is supporting perception. So the extent to which you're oscillating then at 2 Hertz is determining accurate perception of that sensory input stream. We made a visual paradigm of this, whereby what we're doing is presenting basically a visual metronome on screen that is varying either at 1.3 Hertz or at 2 Hertz. So we've got a Gabor patch that is changing its orientation in varying step sizes, either every 500 milliseconds to generate a 2 Hertz rhythm, or every 750 milliseconds to generate a 1.3 Hertz rhythm. What we're then doing is to look in this silent window afterwards at the oscillatory structure that might be generated by these visual rhythms. And we then present a probe at the end of this window. So after effectively 3 silent cycles, we have a probe and we ask them 2 possible questions about it. The first of which is whether that probe was presented on the beat that you might have expected from these rotating Gabors beforehand. So this is your timing task. And the other task was basically, is it presented at the orientation that you would expect that is basically one along from that last one that you saw? And then what we're analysing in this silent window is the rate-specific response. So basically, how much more 2 Hertz power is there when presented with the 2 Hertz rhythm relative to the 1.3 Hertz rhythm, and how much more 1.3 Hertz power is there when presented with the 1.3 Hertz rhythm than the 2 Hertz rhythm. And what Aaron found was that, especially in this timing task, we are indeed finding a sustained response, but that's actually predominating more in these motor areas than sensory areas. So something that I haven't spoken about before is that it's quite likely that all of these timing-based operations in the brain are relying quite heavily on motor structures that can be helping us to send these signals then to sensory cortices. But that what Aaron has therefore found is with the peak in somatosensory supplementary motor area, we're getting this phase locking to these external visual rhythms after they have stopped. Very importantly too, the extent of this phase locking seems to be determining perception. So this rate-specific response we've got on the x-axis here in a figure you can see is not quite paper ready yet. And we're asking how this relates to the D prime in detecting these timing deviations in that probe at the end. And what you see if you look at this red line is that these are going together very nicely. So the people who have this larger rate-specific response in this silent window are the people who can answer these timing-based questions more accurately. To link this part of the talk full circle with the first part of the talk, what we've been further asking about in this data set is basically how exactly this metronome is operating. So I've spoken as if you're saying information has peaks across time, and you're effectively then using this as a sampling window where you're just turning up the volume across your century system because you think information should come in at those particular moments. But in fact, it might be a bit more complicated than that. This temporal structure is also defined by changes in the environment concerning the content. So we know what Gabor orientation actually is likely to be presented. We're presenting these with predictable step sizes. And what we've been interested in is, so this idea then actually put forward by a group, so led by De La Fuente, also with a few others in Mexico, but that actually we might be maintaining this internal rhythm via what they call a dynamic mental imagery. So perhaps we're not just activating our visual or auditory systems in these snapshots across the board, but actually activating the predicted content-based representation at the correct moment in time. So if you've seen this Gabor that's rotating clockwise, then at the particular moments in time, sort of every 500 milliseconds, maybe we're activating this next content-based signal. And this might be even if we haven't got a content-based question about it, we're being asked about time, but we might be still activating these content-based representations. And so Aaron's still finishing off some of the analysis there, but basically the answer broadly seems to be yes. And what I'm showing you here is that actually, we're using an inverted encoding model to ask about these orientation of the representations at particular moments in time, but that those people who have this stronger rate-specific response are also people who have this stronger dynamic mental imagery. So if we're using inverted encoding models to ask about fluctuations in the particular Gabor representation across time, the people who are doing that more are also the people who would have more of this rate-specific response. So we have many questions still about precisely how this is working, but the main takeaway from this study in terms of our broader question is our visual system is tracking temporal structure in the external stream, just like our auditory system is. So to wrap up, what I've shown to you in the first part of the talk is how we might be learning about the statistical structure of our environment in a content-based fashion, so that is causing us to have predictions about what we're likely to perceive, and we're using that learned knowledge to both optimize the generation of accurate perceptual experiences rapidly, and also optimize our ability to perceive that sensory information that tells us our models need updating. So we've tentatively proposed the preemptive processes might be optimizing this former function, so generation of accurate rapid experiences, and a reactive process, the latter, only for the most surprising information. And this type of account could resolve these discrepancies between Bayesian and cancellation accounts that are currently out there. We have support at the moment via some EEG decoding and laminar MRI, but as I say, very much a work in progress. Second part of the talk showed you how we can also predict when important information will be presented, and how those predictions about when important information is presented can determine oscillatory processing in the brain and subsequently fluctuations in perception across time. And we're predicting according both to motor-generated sensory predictions and externally generated ones, which can potentially reconcile these ideas between the flexible and the fixed rhythm accounts. So thank you very much to those who led the work. So focus very much on work that Daniel conducted, Aaron conducted, and Emily, but also with much help from the rest of the team. Thank you very much to the collaborators, so many from UCL, including, importantly, Peter, Matt in Cambridge for the speech work, and Floris, amongst others across this broad line of work. Thank you to the funders and you for listening.
Brilliant. Thank you, Claire. So let's give you a round of applause. Thank you so much.